two talks are coming from Professor Harold Kim's group, and Jeong will lead us off talking about DNA melting influence looping.
Hi, my name is JJ. I work with Harold Kim at Georgia Tech, and I'll talk about how melting of DNA influences DNA looping. So our research is initially motivated by what's called the flex hinge mechanism of DNA looping. And this was introduced by Yang and Marco back in the days in order to explain high looping probabilities of short DNA molecules. And the idea of this model is very simple. A single-stranded, partially separated region can be formed within double-stranded DNA due to double fluctuations. And the probability of having a bubble formation is about 10 to the negative fifth power. So they are very rare events, but still they do exist in nature, even at temperatures way below the melting temperature of DNA. And as I talked about earlier, this model can explain the high probability of looping of short DNA molecules. And here I have a figure of J factor versus length. So the J factor is essentially a quantity that is proportional to looping probability of a polymer chain. And we have a solid line curve here representing the theoretical elastic rod model of DNA. And as you can see, this decreases as the length decreases, meaning the chain becomes steeper and harder to form a loop. And these hollow circles are experimental data from DNA molecules, and they start to deviate from this solid line curve, indicating as the length is shorter, their flexibility increases more than the theory. However, this can be compromised by incorporating this flex hinge model, and these dotted lines are predictions from that. And we have several different dotted lines indicating several different initiation energy of formation of bubbles. So the lower the energy to form bubble, the more easier for the chain to have bubbles, and hence it will promote DNA to loop more easily because bubble essentially is softer than the double-stranded regions. So this idea of bubble-mediated melting is great and it works. However, it still needs some experimental validation. And our research is designed to see whether this idea of flex hinge mechanism is realistic or not. So we began this by preparing DNA samples that are based on what's called two-state model. And the two-state model is essentially can predict the sequence dependence of bubble formation. So here I have an example of the two-state model calculation of short piece of DNA. And on the x-axis, you can tell the sequence content, and the probability of forming a bubble varies as sequence. So using this model, we came up with two groups of sequences, one being meltable and one being not meltable. And actually, these are the probability plots, or mean probability plots of eight different sequences for each. And the meltable sequences have a probability pattern that looks like this. Especially in the middle, they have a high probability of bubble formation, meaning this region is sensitive to form bubble than other regions. And as a comparison, we have non-meltable sequences which have overall low probability of forming bubble. And by comparing these two sequences' looping probabilities, we can maybe study how melting affects looping. And we do that by using a famous single molecule technique called FRET. To briefly go through, we have a DNA molecule, and they have single-stranded stick ends at the ends, and we label this DNA with donor and acceptor flow force, and we attach them on the surface, and excite the donor molecule, and as one end gets close to the other end, they will anneal and form a loop, and energy will transfer from the donor molecule to acceptor molecule. Hence, you can tell whether this DNA molecule is in loop state or unloop state. And by collecting this first passage times of many molecules, we can construct a cumulative histogram that looks like this, which can be fed into a single exponential function, so we can get rates. So in summary, I talked about the flux hinge mechanism, which was initially proposed to explain the enhanced looping of short DNA. But this, again, needs some experimental demonstration. So we used single molecule FRET to measure and compare looping probabilities of DNA sequences that have meltable or non-meltable regions. And we repeated this experiment in various salt and temperature conditions. And also we have different molecules with different size to thoroughly examine whether the effect of melting will exist or not. With that, if you have any detailed questions or curious about the results, please come to my cluster tomorrow. I'll be more than happy to talk about the results. And I'll lastly thank my advisor, Howard Kim, and my lab members, and school and funding. Thank you.
Okay, we have time for some questions. JK?
I have a first one question.
Yes.
What's the physical origin of this stabilization energy for the bubbles? Why is the DNA, what's the molecular origin for it?
So the thermal fluctuation basically can lead to transient opening of bubble base pair disruption. So that leads to forming a bubble.
But those energies look pretty big, so I'm just curious what gives that. It looks like big numbers of stability that you need for it, right, in order to open.
Yes, so basically the probability is very low in terms of free energy. It needs about 9 kT in terms of kT, 9 kT to 12 kT to initiate a single base pair opening, depending on the sequence. So, and what the Yan and Marco, the group from University of Chicago, they suggested that even with rare events of forming a bubble, they can maybe affect looping probabilities.
So based on these numbers, do you think that in the real world, where DNA really have to make these loops, they actually use some proteins or stuff like that to actually work around? Or is that going to be just sort of
So that's what we're trying to do experimentally, and that result is shown in my poster, whether they really do something different on the looping dynamics.
Okay, so from your sequence, you actually had a Tatabox sequence, right? Exactly
Yes.
where the melting was,
Yes.
right? So I guess that's intended, and it seems interesting that the melting probability increases where the Tatabox
Right,
is.
right. In general, melting the two-state model predicts that TR-rich regions has higher probability because they have weaker bonding than JC base pairs.
Okay. And do you actually see dynamics back and forth, or do you only see it latching and one
Back and forth meaning like open and close? Or?
opening and closing?
So there's no way you can really tell whether this is opening or not because it's too quick and too rare. So we tell it by looking at the looping rates to see if, so in principle, if they form a bubble, they will be we'll having a softer region, so maybe sensitive to looping rates. So.
Okay. Questions? Not?
Well, without seeing the thunder of your poster, do you see a difference with this sequence or not?
That's what I'm trying to sell.
Okay, well,
in short, it's not obvious.
Okay.
So come see me tomorrow.